welcome everybody. Estamos re contentas de estar acá, de poder estar compartiendo esto con ustedes. Bueno, nada, tenemos un montón de cosas nuevas para este año. La verdad que pudimos progresar bastante y eso está buenísimo. Espero que me escuchen bien. Yo la verdad no puedo ver el Twitch, no puedo ver nada en este momento, así que estoy como a ciegas hablando y es como raro. Perdón si estoy como un poco nerviosa, pero me parece rarísimo estar hablando a una cámara y no poder ver a todos ustedes en el escenario como fueron los años anteriores. Pero gracias por estar del otro lado, imagino que están ahí. Bueno, tenemos una agenda, ahora voy a pasar de slides, bastante completa este año. Nos ayudó el hecho de que no hay barreras, por decir de alguna manera, y pudimos incluir chicas de todas partes del mundo. Literalmente tenemos speakers en Australia, en Europa, en Estados Unidos, en Argentina, en distintos países de Latinoamérica. Así que nada, eso está buenísimo. Son 17 charlas en total. Tenemos 2 tracks, como pueden ver en el slide. Todo lo que sean las charlas de track 1 van a estar en este Twitch, en el que están ahora. Y para las charlas del track 2 van a estar en twitch.tv/.picon2, ¿sí? Básicamente como este Twitch, pero con el 2 al final. Bueno, la mitad de las charlas está en inglés y la mitad en español, pero ahora les voy a contar sobre la traducción que tenemos, así que eso va a estar bueno también. Bueno, la introducción que suelo hacer siempre a este evento, que muchos por ellos la escucharon antes, si fueron a alguno de nuestros eventos anteriores en persona, desde las 2 ediciones anteriores, es que este evento lo hacemos porque creemos que hay un montón de chicas que tienen cosas interesantes para presentar, creemos que todas tienen investigaciones interesantes para contar y compartir. A veces ya es un poco difícil hacerlo por ahí por primera vez, por ejemplo, en un escenario mixto, donde muchas veces una es la única speaker mujer y a veces se hace como un poco difícil afrontar esa situación, una se siente como el bicho raro. Entonces, bueno, decidimos hacer este evento donde creamos un escenario más confortable y donde le damos todo el apoyo y soporte a las chicas. Muchas son speakers por primera vez y a otras no, otras tienen mucha más experiencia. Esperamos aprender de ellas, esperamos aprender de todas y bueno, y que ustedes también disfruten del evento del otro lado. Bueno, ahí les dejo la agenda. Recuerden que los horarios están todos en GMT-3, que es el horario de Argentina. Así que bueno, estimo que tenemos gente ahora de todas partes del mundo. Ayer había gente de España también, que bueno, son como 5 horas adelantado. Así que bueno, les cuento sobre el Discord que tenemos. Si todavía no se unieron, es ahora el momento para hacerlo. Ya están todos los canales abiertos. Ahí les dejé en el slide algunos screenshots de las secciones que tenemos. Hasta ayer estaba solamente habilitada la sección de info, donde estaba el lobby y ya había gente hablando. Ahí vamos a tirar anuncios y cosas importantes, así que presten atención al canal de anuncios porque vamos a tirar algunas cosas interesantes durante el día. Después tenemos también el canal de CTF, que es para, bueno, discutir todos los que están jugando al CTF. Ayer había ya más de 50 teams jugando al CTF oficial que tenemos. También tenemos otro CTF de ASAP, de uno de los sponsors. Ahora les voy a contar un poco más de detalle. Pero bueno, todas las discusiones que se presenten ahí, pueden discutirlas en el canal, lo que sea, que quieran compartir. También tenemos la parte de charlas, que ahí pueden hacer preguntas, como ven en el slide tenemos un canal para preguntas del track 1 y preguntas del track 2. Algunas de nosotras vamos a ir leyendo las preguntas que ustedes tienen ahí para al final de la charla hacerle las preguntas a cada speaker, ¿sí? La speaker directamente no va a estar mirando ni el chat de Twitch ni el Discord porque hay como un delay de 30 segundos en la transmisión que es bastante confuso, así que nosotras nos vamos a ocupar de eso. Pueden hacer las preguntas en el idioma que quieran, sea en inglés o español, y nosotros las vamos a traducir para la speaker. Como dije, la mitad habla en inglés y la mitad habla en español, así que bueno, nos vamos a ocupar de eso. Después también está en Discord toda la parte de los sponsors. Tenemos canales para los sponsors que van a estar ahí compartiendo información, algunos tienen challenge y demás, así que los animo también a visitar los canales de cada uno de los sponsors. Y después tienen el canal general, donde, bueno, tenemos un canal para hablar en español y uno en inglés, y después un poco relacionados a los temas de seguridad informática, así que, bueno, nada, están totalmente invitados a participar en el Discord. Bueno, ¿qué más tenemos? Para este año tenemos Live Translation, como les comentaba recién, lo cual es un progreso para nosotras genial. La verdad es que el año pasado lo quisimos hacer porque teníamos una charla en inglés, pero no pudimos. Este año se nos dio gracias a Faraday y a My Translation, que bueno, es la empresa que hace las traducciones, y son unas chicas re buena onda, la verdad. Estamos re contentas de poder contar con ellas, y se van a estar ocupando de hacer la traducción del track 1 de inglés a español y de español a inglés, dependiendo el idioma de la charla. Así que la gente que habla en inglés también puede ver las charlas, escuchar las charlas en español. La idea es que se unan al canal de voz que está acá en el slide, así que se unan a ese canal y escuchen el sonido de ahí y silencian el Twitch para ver solamente lo que se transmite en imagen en Twitch y escuchen el audio desde el canal de Discord, que es donde está la traducción, ¿sí? Bueno, otra razón más para unirse a Discord. Otra cosa que tenemos este año, que el año pasado no tuvimos, es el CTF. También un gran avance por nuestro lado, que realmente queríamos hacerlo, queríamos contar con un CTF ya desde la primera edición y no habíamos podido hacerlo antes. Ahora, gracias a las chicas de Cyber Yuxu, podemos tener un CTF, ellas lo hicieron y la verdad que hicieron un trabajo excelente. El CTF está buenísimo, como dije, ya tenemos como más de 50 teams jugando. Ayer se habilitaron algunos challenges, ahora se habilitaron algunos más, de a poco se va subiendo el nivel de dificultad, así que nada, tenemos también premios bastante interesantes, tenemos kits de Raspberry, de Arduino, licencias de Pentester Lab, hay un montón de cosas, así que nada, les animo a jugar. También tenemos el CTF de uno de los sponsors, de ASAP, que también estaban ofreciendo premios interesantes, unas YubiKeys y otras, entre otras cosas, así que también los animo a participar en el CTF de ASAP. Y por último, tenemos también Swag este año, que es algo nuevo que también queríamos hacer y bueno, no habíamos podido hacerlo antes. Ahora pueden comprar stickers, remeras, buzos, lo que sea, de Bits, que es nuestra mascota, el conejo que nos tiene in love a todo el mundo. Así que bueno, el único detalle de nuestro shop es que por ahora solamente soporta envíos en Argentina. Prometemos que para el año que viene vamos a tratar de buscar alguna solución para poder hacer shipping del merchandising a otros países del mundo. Pero bueno, por ahora pudimos hacerlo para Argentina, así como la gente de Argentina tiene la posibilidad de poder comprar algunos stickers, aunque sea, o alguna remera o algo que les guste con nuestro conejito. Bueno, obviamente voy a agradecer a los sponsors. Todos los sponsors del año pasado nos están acompañando también ahora, así que muchos de ellos pusieron premios para el CTF, entre otras cosas, nos ayudaron con un montón de cuestiones de este nuevo formato de evento online, así que muchas gracias a los sponsors del año pasado que están acompañándonos ahora también. Y tenemos nuevos sponsors este año, tenemos a Napsys, a SAPS, a Hackmetrics, Arsex, Infosec Argentina, tenemos varios sponsors nuevos, y está buenísimo que más empresas nos estén ayudando en esta iniciativa, porque realmente nosotros, como ya saben, no cobramos entrada, el evento es libre y gratuito, así que todo lo hacemos a pulmón además, y está bueno contar con el apoyo de las empresas que nos puedan ayudar a hacer todo lo que tenemos que hacer, ¿no? Porque realmente llevar adelante un evento es mucho más trabajo de lo que uno se imagina en principio, y uno suele tener también muchos más gastos de los que por ahí había calculado. Pero bueno, gracias a los sponsors podemos hacer esto realidad, así que muchas gracias a todas las empresas que nos están acompañando. Bueno, no mucho más para decir. Una cosita más que me estaba olvidando y que no la pusimos en el slide es que gracias a HackerOne y a No Starch Press, la editorial de libros, tenemos un descuento del 30% para todos los asistentes del evento. El código de descuento lo vamos a estar tirando en nuestro Discord en unos minutos, así que otro motivo más para sumarse al Discord. Muchas gracias, HackerOne y No Starch Press, por este súper descuento. La verdad está muy bueno porque además somos todos nerds seguramente y nos encanta leer libros, así que lo vamos a aprovechar un montón. Bueno, sin más preludio, saben que tenemos una keynote de lujo este año. La verdad que estoy re contenta, estamos todas re contentas de poder contar con Marion para la keynote. Marion es parte del equipo de Intel Storm, y la verdad que, nada, tiene muchísimo conocimiento, hace muchos años que trabaja en esto, y se armó una charla espectacular para el NotPinCon, así que va a ser nuestra keynote y estamos realmente muy contentas y realmente esperando con ansias ver su charla, que la va a dar en live ahora, y para eso son como las 6 de la mañana, así que es un esfuerzo grande que está haciendo y de verdad le agradecemos un montón por haber aceptado la propuesta de ser Keynote de esta edición de NotPinCon y estar acompañándonos. Así que bueno, sin más, saben que cualquier cosa pueden encontrarnos en Discord, vamos a estar acá, y let's welcome Marion.
Hello. Is it my time to speak? Yeah, okay. Hello, hi. Good morning, everybody. My name is Marion, and I welcome you to the keynote today about how curiosity killed the cat. I'm a reverse engineer, and over the past 10 years, I fought a lot with source code, and recently with compilers and with CPUs. And there's lots of peculiar learnings to be found when you go down that rabbit hole, and that's what I'm going to be talking about today. Also, I want to use this opportunity and say thank you for the invitation to speak here. I'm super excited actually to be speaking in the first place, and thank you for the invite to the keynote. That's a big honor. And also, I'm excited this is an Argentinian event. I have to tell you, I love Argentina. When I was a student about 10 years ago, I did an exchange in Argentina. I lived in Buenos Aires for 8 months. And I forgot most of my Spanish, but it was a wonderful time to be there. So yeah, I'm happy to be here with you today. All right, let's get started. Let's see. First of all, since I work for a large corporation, of course, I have to tell you that the opinions and positions expressed herein are mine only and do not represent the views of any current or previous employer, including Intel Corporation or its affiliates. Who am I? Why am I here? As mentioned, I'm a reverse engineer. I started my career in the threat detection industry. I worked in antivirus and in advanced threat detection. From there, I changed into incident response. From there, became a contractor and then moved into offensive security. And now I work for a microchip producer. And yeah, on that path, I learned a lot about how to analyze binaries, about how to look at the bytecode, about how bytecode is produced, and about how bytecode is processed by the CPU. And I thought that's super fascinating. How did I think this was so interesting though? Like I learned, many reverse engineers and many people who are in binary research. I started out figuring out I have OCD. I'm really interested in sorting things and ordering things and figuring things out and bringing things to an end, and yeah, I would call it a talent. I have a little exercise here. So OCD is a compulsive disorder where you want to see things in order. You cannot look at, like, for example, a stash of colored pencils and not see the rainbow. So if you look at the picture I posted in the slide here, if you share that feeling for order and process, you'll figure out that there is a skin-colored pink pencil that's right in the middle. It just doesn't fit the rainbow, right? So OCD means that I would go and pick that pencil up and put it in the right position where it has to be, because I can't look at it the way it's just there in the middle. And that is something that nags you on a daily basis. And then when I started analyzing binaries, I found my passion. That sounds stupid, but literally in reverse engineering, I found the cathartic effect of just staring. You can stare at code all day and try and figure it out, and you will learn so many little things. Like, you will learn so many little details, and this keeps you content all day. I'm not kidding. I have coworkers who open up either Pro at the end of the day because it helps them it helps them calm down after a really exhausting day at work. And yeah, if yoga isn't your thing, I really recommend get a disassembler. It helps. Fun aside, what did I want to talk about today? So the first topic I want to bring to you is malware research, and actually explain why I left malware research. Anyhow, so if we start looking at the slide on the left side, you will see a beautiful dump of disassembly out of the Radar 2 tool. By the way, yeah, it is 6 o'clock in the morning here in Portland. This is hard. The disassembly we see here is the typical subject of addiction that I mentioned before. Like, if I look at the slide, I have to start reading the code. I have to start analyzing, and I'm sure some of you feel the same way. Anyhow, we're not going to talk about the details of this disassembly today. When I started out in malware research, I thought that malware must be super complicated because, yeah, reverse engineering is hard and malware is dangerous. That's what I was told. And essentially, I found out after some time doing the job that it has to do a lot with guessing and building a hypothesis and constructing a picture about what people what one sees inside of a binary and bringing that to a higher level where you can explain that information to other people. That's essentially what threat research, like what reverse engineering in threat research entails. You figure out what the binary's intentions are, and you try to explain this in a human understandable way. So far, so good. I thought that is very challenging, and it turns out it is, except if people tell you the dirty tricks that are hidden in there. And that's what I wanted to do today with you. I wanted to show you 2 of my favorite tricks in malware research and how to analyze a piece of malware rapidly. First of all, the question, like, how much reverse engineering do threat researchers actually do? So I spent a lot of time in that industry, and I only ever really learned how to analyze binary code properly after I left that industry. I was rather disappointed as a malware researcher, figuring out that it doesn't matter that much whether my results are detailed and whether my results are 100% correct. Most malware research actually wants to get, as mentioned, the bigger picture of what does the malware intend to do, where does the malware intend to go, but not necessarily what kind of buffer size does it use for sending its communication back to the remote server, like how much data is actually exfiltrated, how exactly does the encryption work with which it encrypts files on disk if we're talking about ransomware, and so on and so forth. So lots of detail is now actually spotted by malware research. And yeah, as promised, things that people didn't tell me when I started is that analyzing malware, for the most part, like the large mass of malware is not horribly complicated, and it's not horribly difficult to analyze. There is 2 major skills that I learned over the years that are essential, which is, first of all, you need to be able to unpack it, because most malware, like most like average malware, is heavily packed. So if you can figure out how to unpack it, you have a much easier time to analyze. And a trick, like, unpacking seemed so hard to me until literally I was sitting in a bar in Las Vegas after DEF CON with another malware analyst who said, no, look, unpacking is actually super easy. Like, you find memory, right? You set breakpoints on the buffers that you write to, and you let the thing run. And you try this a couple times. Eventually, you find the buffer where it's unpacking too. And I was like, what? It's that easy? And it turns out, yes. I mean, I'm having a hard time here calling it easy because it's not like a piece of cake, but it's not that hard either. So if you want to try to unpack a piece of malware, yeah, contact me afterwards. I'll send you a heavily packed piece of malware, and you can go and start your luck. Like, find where actual memory writes are happening. if you look at that slide in the center, like the assembly that I posted here, the bottom shows you what I mean with memory write. There is 1 byte that is written to a buffer. The buffer is pointed to by ESI plus EDI. That's what I mean with memory write. Like something is written somewhere, and if you want to figure out how the unpack works, you need to figure out where it is writing to. The big work starts afterwards once it's unpacked, and you actually have to analyze the code that's being written, or like the data that's being unpacked into memory. But honestly, the packers aren't the biggest problem. Now, this is one trick. The second trick that I learned in threat research is that people writing malware are developers. So they are using code, like they're using the regular development methods. And a lot of them actually use, just like most of us, Stack Overflow for figuring out how to solve specific problems. I kid you not. You won't believe how much malware I analyzed by just copy pasting APIs that I found in the malware into Google. And Google would point me to like your preferred search engine, and the search engine would point me to pieces of code that other people published on the internet, and they're like, hey, if you want to implement a keylogger, here's what you need to do. So reverse engineering in those cases essentially turned out was reading source code from the World Wide Web that ended up in this piece of malware. And it sounds easy if I say it here. Not all malware is that simple, not all problems are that easily solved, but a lot of them. So yeah, if you want to go ahead and speed reverse engineer a piece of malware, look for memory writes, set breakpoints, dump the buffer that's being written afterwards, load it into a disassembler that can parse, that can find you the symbols that are being used in there, like the APIs that are being used in there, and punch them into Google and see what comes out. I bet 50% of malware samples that you can find, you can analyze that way. All right, but I'm talking here like it's all that easy and everything's smooth and shiny, and it is not. There is complex malware out there. There is lots of abstractions that make reverse engineering malware difficult. But I ask you to think about one thing. So imagine, for example, you look at an average browser. You go ahead and try to reverse engineer Firefox. Just as a random example. You will be busy for the next years. There is, like most commercial software that's out there, almost, as I call it, real software, is built to last, built to scale. There is lots of different features in there. There is a user interface, there is a backend, there is, I don't know, so much stuff inside of that software that malware just doesn't have and that malware just doesn't need. Most malware samples are rather small, and you might have noticed in the last slide, most malware developers are not actual software developers. So like they don't build really big applications. They don't build lots of error handling functionality. They don't stash a million features in there because they don't interact with the user most of the time. So malware by itself is not as complex as real software. And if you look at the classical business model of a malware user, like someone who uses malware to breach other people, they also have no interest in building highly complicated software. Granted, there are some malware users out there who are interested in proper software development and build like complex things, but your 95% of malware is not great software. As mentioned, it doesn't need to be. If you look at the return of investment in the malware business, if malware developers would spend a year and a half on developing one piece of malware, they would need to make a lot of money afterwards to pay the bills, right? Yeah, stupid example, but it's not in their interest to spend a lot of time in writing really complex malware. That's what I'm saying. Other peculiar learnings that you come across when looking at binaries, it feels a lot like looking at other people's code. this is something I found out a couple of years into the job, that like I'm essentially looking at something someone else came up with, like their brainchild, and I need to figure out like what they thought when they wrote this piece of code that I'm trying to figure out. And that is very weird. It becomes like, yeah, peculiar. Some of the malware authors will start implementing a feature and not actually finish it. They will build in debug prints that, of course, aren't printed when the malware really executes, but as a reverse engineer, you see like everything that goes into this piece of binary. So sometimes you find really funny things in there. And one of the rabbit holes I wanted to share with you today was if you ever like run into a binary analyst, like preferably a malware analyst, walk up to them and whisper Delphi in their ear. It's a thing. Fun story, a couple of years ago when I was working as a reverse engineer for an incident response company, I was sitting there in the room with my coworkers and we're happily working away. And all of a sudden our team lead comes in and says, look, we have a new case coming in, and yeah, we need you guys to figure out the binary really quick. And it was written in Delphi, and the whole room like goes and stares at him and is like, what? Like, no. Some people start laughing, some people like quietly sneak out of the room, and yeah, it's hilarious. Why though? Delphi is not the only programming language that does that, but Delphi in particular produces really, really awkward binaries. There's tools that help people analyze them. Of course, if you've written Delphi before, you have an easier time reading those binaries, but altogether, Delphi is just not nice. And again, there's a couple peculiarities that you come across in binary research that's just like Delphi. Visual Basic 6 bytecode. Anyhow, let's move on. The next thing I stuck my nose in after threat research was I ended up working in incident response. And being a reverse engineer in incident response is quite a lot different than in threat research, because all of a sudden your results matter. What do I mean by that? Of course, threat research's results are important too, but in incident response, the questions that you get are just much more specific, which means as a reverse engineer, you need to really, really care about detail. And I love that. All of a sudden, there were requests like, oh, could you extract this compression algorithm from this piece of malware? You want to figure out how it unpacks. Or can you analyze this ransomware like really, really quickly? We need to figure out how it spreads across our shares, or how come that this malware is all over our network on different machines. And then, yes, all of a sudden you need to look very, very closely. Again, in threat research, detailed reverse engineering isn't really much of interest because it takes a lot of time. Reverse engineers are expensive. And what matters mostly is to understand the big picture. And in incident response, all of a sudden the small pictures matter too, which I loved. One of my favorite questions there was to prove that something was being done, or to prove that something was not being done. Like, we have a piece of malware, and we want to know, is it the only one that we have here? So we see certain activities that happen on machines in the network, and we have this one binary, and can this one binary do all of these activities? That's a very important question. That's usually something people want to have answered quickly, so then reverse engineers have to work like fast, which is a very different work environment too. And all of a sudden you find yourself in a position where you have to be sure that this one piece of malware can do all these malicious things, which is very, very different from just creating a big picture analysis. So much fun. Anyhow, let's close the malware chapter. Over the years, so now I don't do all that much reverse engineering anymore or look at malware, but I still get people asking me like, how did you get in there? And for once and for all, I wanted to document that. You need to practice a lot. There's a lot of things to read. Then you need like 10 times as much practice, and then you'll be a reverse engineer. On the left side of the slide, I put a list that I sent to all these people. So people ask me, how do you get into that? And they're like, no problem, I can give you things to read and exercises. So I sent them exactly this list. You need to study some assembly. Like without reading assembly and without understanding assembly of the architecture you want to reverse engineer, you're gonna have a very hard time. You need to understand functions and stack interaction. You need to understand executable file formats and a bit about loaders. Like you work with your disassembler, then you work with a debugger, and there's something happening in between, and it might be good to understand the basics of that. Then, of course, you need to understand something about the operating system you work on, about process and threads and memory management basics and the OS API and basic OS services. Like if the binary calls like fopen, what exactly happens on the operating system side is good to actually understand. And then we have the analysis tools, and that's pretty much it. It's a lot, but the list sounds very cute, right? And yeah, you read about that stuff and then you go practice. And in reality, it's of course not that simple. There's a lot of time that goes in there. There's a lot of nitpicky little details that are necessary to understand. If you look at a specific binary that comes out of a specific compiler and wants to run in a specific context, and the learning curve is very steep. But it's fun, I'm telling you, and it's very, very relaxing and cathartic. Good. Let's move on. Eventually, I left malware research. That was when the big surge of ransomware came up. And all of a sudden, I found myself looking at tons and tons of ransomware. And if you've seen one, I promise you, they're not getting any more exciting. So I eventually got an offer from Intel to work on microarchitectural security. Of course, I couldn't just not go there because I mean, I was an x86 reverse engineer, and all of a sudden the mother company of x86 telling me to do security research. So this is how I ended up doing offensive security research and got to look a lot on how instructions, first of all, are being produced, and second of all, are being processed. And I thought that was so fascinating. So let's have a look at that. Working at Intel, I spent some time on compiler internals, more specifically on GCC. And GCC now, GCC and me now have some sort of hate love going on. Like I love the compiler because I understand this little bit of it, and I hate the compiler because it still doesn't actually exactly do what I wanted to do. But that's a different story. GCC by itself, I counted once at the time of where I was working on it, was a total of about 14 million lines of code. And if that sounds a lot, it's because it really is. It's huge, humongous. And it's been organically grown since 1984, which makes it huge and complicated. GCC, like most compilers, has a front end, a middle end, and a back end. And this view of the compiler is like from a very, 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 very distant view. And what's interesting about that, what I wanted to be talking about today, is how the compiler parses the representation that it has of the source code into the actual byte code. Like how is the machine code produced? This was something that I was looking at for a long time, and it's super fascinating. Honestly, I could be talking about GCC for hours. I'm not going to do that now, but we're going to go into details very soon. Just to have you see like how the compiler looks from inside. It's not very pretty. It's a lot of different passes. The GCC is organized in passes. This slide, do not try to read it all. It shows you a list of passes that are executed inside a compiler. And if you try to interact with the compiler from inside, like modify the compiler or insert a plugin, what you essentially do is you figure out a path where the things that you're interested in are happening and work in that path or before or after that path, which makes it sort of approachable, to put it like that. It's not easy, but it's an approachable topic. And yeah, as mentioned, what I wanted to be talking about today is how instructions are made. So yeah, as a malware researcher, I spent lots of time looking at instructions, but it never occurred to me to just go and figure out like how did he end up inside of a binary. It turns out it's a very fascinating process. Basically, what happens when you compile a binary is that your source code is translated to one or more intermediate representations. And from there, the compiler produces assembly, and from assembly, the bytecode, and the bytecode eventually ends up in an executable. It's a very high-level view. The interesting part about that is that before the intermediate representation, we're architecture agnostic, more or less. So if you have C code, you can compile a C code to ARM, you can compile a C code to x86, you can elevate that C code into a different representation and make it something else. I don't know where I was going with that, but anyway, like before you parse it into IR, it's solely architecture agnostic. And after that AR process, all of a sudden we have something architecture specific. So from the different intermediate representations, at the end what comes out is a binary that runs on this one machine we compiled it for, or possibly a different machine if you go for cross compilation, but that's a whole different story too. So the process that's so interesting about that is in GCC, most of the intermediate representations that there are still language specific. If you look at the first two groups, like the generic representation, the chimp representation, they kind of more or less look a bit C-ish. They're more or less human readable. But then there comes the fascinating part, which is RTL, the register transfer language, which is not readable. It's nothing like C. It looks a bit like a descriptive language that tries to describe the bytecode that is produced afterwards. And that's fascinating. So RTL is a number of passes in GCC's compilation process, and the language itself changes as the compilation process steps along. If you're interested, you can tell GCC to dump the intermediate representations. There's a debug flag for the compiler, which makes it dump all of the different representations in the different passes. It's a lot of files. Anyhow, so RTL itself is a language that changes as execution continues, or the representation of your RTL view changes. And if you look at the different RTL stages, you can see how the language massages the very abstract machine language into very specific machine language. The eventual translation stage into assembly, which is, by the way, text-based in GCC. So GCC produces ASCII files that are temporary assembly listings, which are then compiled to bytecode. And GCC translates the RTL into the text-based bytecode and text-based opcodes using machine definitions that are very architecture specific. How does it look like? RTL is fun. It's kind of, it looks Lisp-y, like it looks like Lisp. I personally have never worked with Lisp, and tries to describe how assembly needs to look like for a specific architecture. If you look at the stash of text, it won't tell you much, but I marked the important things, which says set di, in our case it will be RDI, to hold a certain pointer to a string, and then call put string, like the library function. So this is literally printing hello world. And yeah, I love staring at those listings. It's my thing. The machine definitions that GCC uses to translate this this representation of assembly to machine code look as follows. So like there's a huge file for each architecture that GCC understands that literally define how a certain RTL instruction is supposed to look like in the assembly listing. And yeah, that's fascinating as well. Then from this stage, what you get is a text file. I was surprised looking at GCC and eventually finding myself like looking at text files. So once the compiler is done, it produces a temp file that is very much ASCII based and looks, as you can see on this slide. There is some assembly in there and a lot of instructions for the assembler on how to produce the assembly. Eventually, this text is being read by us, like the GNU assembler, which then produces the bytecode, which you see on the right side. Isn't that awesome? I spent a lot of time in GCC and couldn't stop staring at this process. And yeah, I eventually understood how the bytecode ends up in the binary that then the disassembler picks up and tries to disassemble and represent as opcodes again. Yeah, that was my personal favorite rabbit hole. But then, now we have bytecode. What happens with the bytecode? Eventually, we'll have to feed the bytecode to someone, right? And that happens to be the CPU. So once you execute the binary, of course, there's lots that the operating system does and a lot that happens in between. But eventually, these bytes, the bytecodes that you see in the binary, ends up being fetched by the CPU and eventually causing the state of the architecture to change. What am I talking about? On the next slide here, you'll see a very, very simplified block diagram of the Intel Core architecture. You can imagine Intel won't like it much if I talk in great detail about this, the architecture, but I'm very happy they allowed me to show you this simplified image. Essentially what the CPU does is it goes ahead and fetches instructions from the instruction cache, which is usually in the L1 cache or always in the L1 cache on Intel architecture. It decodes this instruction, it executes this instruction. It might or might not interact with the memory subsystem, and eventually reports back the results. This is like a 10 million foot view on what the CPU exactly does. There is a lot going on in this process. Most importantly, most architectures nowadays work with parallel execution, which means there's more than one core in the architecture that can execute things, and the instructions are reordered so that they slip through the execution phase faster. And on the next slide, I have a picture that's even a little more detailed. CPUs advanced a lot over the past decades, like a lot. And these graphics you see here are very, very high level. Essentially, every component that you see in this picture is really complicated. There is teams of people working on implementing how a single buffer is handled by the CPU. I kid you not. For us as reverse engineers, what's interesting, if we look at these graphics, is if you reverse engineer a binary, you look at one instruction after the other, right, and you try to figure out what's their context and how they interact with each other and what happens after what and so on and so forth. And in reality, the CPU isn't all that much invested in law and order of which instruction follows after which. As mentioned, there's a lot of parallelization going on in the core. So essentially, our instructions are taken from the instruction stream, they're mingled and reordered and resorted. The CPU figures out like which dependencies exist and which don't, and then takes the stream and basically puts it into buckets and executes the different buckets at different stages. And it's beautiful that at the end of this, we still have the binary executed like instruction by instruction, while in reality, that's not actually what's happening. It's really, really fascinating. And if you're interested in that, I can recommend you go to wikichip.org. Wikichip.org explains in much greater detail than I can tell you today about how these different components inside of the core function. It's a very, very fascinating field. Personally, in my career, I spent less time on the different components in the core and more time with the individual instructions. And one thing that I can just really recommend is if you're interested in how instructions are processed by the CPU, fetch the Intel software developers manual and look at the documentation of an individual instruction. is really fascinating, because these instructions come with high-level descriptions of how the core executes them. If you look on the left side of the slide, I posted a screenshot of the STM showing the VMX on instruction. I actually spent a lot of time looking at that instruction and inside of the instruction. It's really fascinating because it helps you understand the different modes that a CPU executes in, and understand the language in which the manual is written. The important things you can see in VMX on, or specifically in Intel's virtualization, is the concept of CPU execution modes. VMX on enables virtualization on the machine, or enables the hypervisor, and in that action, the CPU switches into a different mode, and different modes in CPUs mean like entirely different worlds for instructions that execute and what they're allowed to do and what they're not allowed to do. This is how privilege separation is implemented in the core, and yeah, it's fascinating. Also, what I needed to learn, looking at the individual instructions, is that nowadays on x86 instructions operate more like functions. If you've ever executed a CPU ID instruction, you have noticed that you have to give it an argument. You have to tell which leaf of that instruction you want executed, and the instruction behaves a certain way, given different input operands. And it turns out that many instructions have this behavior. So depending on which context they're executed in, they will exhibit different behavior. And this is because the core interprets an instruction differently in different execution modes and given different arguments. It's really, really fascinating too. All right, this much about CPU internals. Finally, the last topic I want to talk about, and I think I'm running out of time anyway, is fuzzing. After all these adventures in compilers and CPU internals, a different topic landed on my table, and I'm telling you, my manager loves to throw different topics at me because I'm like, oh my God, what's this? It's new. And eventually this year, I started looking into fuzzing, and I've never fuzzed anything before, so that was really interesting. The thing I can recommend you is, if you work for a CPU manufacturer, is fuzzing is fun because you can get CPUs. I have 2 Xeon boards. And as you can see on the screenshot, these Xeon boards have a lot of cores, and the more cores you have, the more fun fuzzing actually is. And yeah, just recommend it. A quick 1-minute introduction to libfuzzer. Libfuzzer piqued my interest because it is so flexible. You can modify it in many different ways, and it's rather easy. It's rather straightforward. Essentially, what you want to do if you fuzz something with libfuzzer is you pick a target. Of course, you need something to fuzz. This thing you want to fuzz needs to be able to interact with something outside. I put the big, if you fuzz a library, you have lots of APIs that you can fuzz, lots of exported functions. If you fuzz a piece of firmware, you still have interfaces you can interact with. It's just a little bit more difficult to get there. I'll just leave that here. Anyhow, once we have the target, we need to write a harness. We need to have some piece of code that, as mentioned, does this interaction with the target we want to fuzz. You need to compile things appropriately, and honestly, you won't believe how much time I spent lately on compiling things that can turn out fairly complicated. I'll just leave this here too. And yeah, eventually you run your fuzzer and you start collecting crash dumps. And while this sounds very easy, it might as well take a couple of weeks until you get going and productive in the scene. But yeah, the interesting part is collecting the crash dumps, and that's a lot of fun too. I wouldn't be who I am if I wouldn't want to look at the internals of libfuzzer as well, because my inner squirrel can just not know how exactly libfuzzer works. So I spent a little bit of time on reverse engineering it. I think I'm running out of time, so I'm not actually going to go into details here. But I can just really recommend, if you're interested in fuzzing, don't just go and use the tools. Go and understand the details of how these tools work, and it's magnificent. I promise you. What I find fascinating about libfuzzer is it's essentially instrumenting your compiler. So you're compiling with libfuzzer and tells the compiler to put certain callbacks into the binary to report back to the fuzzer what exactly is happening while the binary is executing. That's not just libfuzzer, that's also the sanitizers that come with LLVM. Many thanks to the people who wrote those, they're amazing. And yeah, once your binary is properly instrumented, it literally talks to libfuzzer. It reports back to the fuzzer of what exactly is happening when a certain input hits a certain function, like which edges are executed and not. And what I found very interesting is like if you compile a binary with the sanitizers and the coverage set to indirect, where's the function on that screen? I can see right now. But if you tell the sanitizer to cover all the indirect calls in your binary, then with cross-references to that sanitizer callback, you can find all the indirect calls like with one click inside of IdaPro. If I had known that as a malware reverse engineer, that would have been very interesting to study how indirect calls are actually landing in the binary and where does the compiler decide to put them and where does the compiler decide to not. Yeah, that's another interesting rabbit hole I never went down but would like to. And of course, yeah, they help you to profile binaries, and it's really interesting to try to visualize the profiler, to analyze your inputs, and yeah, I can only recommend that as a project for someone who's interested as well. Finally, I think that's my last two slides that are coming up here. Inspectability, automation tooling, and the things that I learned are the most important things in binary analysis and overall in infosec research. If you can't inspect something, you can't analyze it. If you can't analyze it, you can't tell other people what it does. You can't tell other people where the bugs are. You can't learn. And that's essentially just a lose-lose for all of us. So you want to inspect. Automation is important too. We can't scale humans, but we can scale computers. And yeah, tooling. For me, most of my experience in offensive security research was tooling, like writing compiler plugins, writing fuzzers, writing scripts to automate. And essentially, that's a very important part that's heavily underappreciated. Of course, offense feeds defense, but we have very lively proof of concept culture, and the proof of concept is not the same as an actual attack. Things are hard to verify. The more complicated or more complex an environment is, the harder it is to verify something, the harder it is to be sure about something, the more important it is to write a proof of concept that actually works. Interdependencies, human error, and confirmation biases are issues we all fight about, and the more people are working on a topic, the more human error there is, and the more confirmation bias that comes up. And yeah, something about security research that had to learn as well is that if you look at something and there isn't a bug yet, then there could be a bug tomorrow, which again is why we need more automation, proper tooling in our sector. Finally, wisdom condensed complexity is a real assumption that toxic inspectability is important. As just mentioned, tooling is hard. That's the 4 important pieces that I learned over the past 10 years that I really learned to embrace. Finally, the OCD, 10 years in, I still can't stop sorting things. That's a damage for a lifetime. Anyhow, I'm done with my presentation. I thank you all very much for your attention. It's kind of weird not seeing an audience in front of me. I think I went over time by about 5 minutes. I'm sorry for that. I don't think we have time for questions. But if you want to ask something, hit me up. My Twitter messages are open, or ask in the Discord, and I'll answer in there. Thanks so much.
Yeah, thank you so much, Mario, for this. technical stuff. We love technical stuff. And I'm sure a lot of people in the audience loves reversing and assembly. So we really enjoy your talk. And checking the chat right now, a lot of people is just saying thank you so much. I'm looking for questions. I have one here. Matt asked, if you could pick only one resource to learn about reversing and malware analysis, which one it will be?
Install an old version of Visual Studio, preferably Visual Studio 2012. That's my favorite. Write a few simple applications with simple control structures, like an if-else and a switch statement and a few different loops. Compile these without optimization settings. Get a disassembler and start staring. There is nothing you can read that will get you there quickly. There's no tutorial that can teach you the skills in a quick and comprehensive manner. You need to start on the practical side, and from there figure out what you don't know, and then you go and look for stuff where you can read about things you don't know.
Yeah, that's absolutely true. The practice is just really important. So thank you so much. I believe there are no more questions, or at least I'm not seeing them, neither in the Discord nor the Twitch chat. But as Marion said, you can just go to Discord and ask some questions there. Also, I believe that the slides are going to be available for you. So I hope you enjoy this talk, and we are just moving to the next track in a few minutes.